Okay, so you were just watching two videos from Khan Academy about what is a differential equation and then how to write a differential equation. So here we have a differential equation. So the logical next step is, well, how do we solve a differential equation? So for right now here in chapter 11, we're only going to be looking at differential equations that are separable. So this can be separated. We can get the s's to one side and the t's to the other. So the variables that are in the derivative here, the s and the t, what we want to do is we want to get them to different sides of the equation. So if we can separate them, then we can solve this. And remember from the Khan Academy video, the solution is not going to be a value, it's going to be a function. So we are going to go ahead and have a look at this, and we are going to try and solve this. Okay, so we are going to be solve a separable differential equation. So that's what we're going to be doing. So we're going to start by solving this one right here. So our example is we're going to solve this one, ds dt is equal to k. And remember, k is just a number. You know, we could like put in the number 10 or something like that over s squared. So when we solve this, what we want to do is we want to get all the s's to one side and all the t's to the other side. So it looks to me like it would be easiest to get the s's over here on the left and the t's over here on the right, because I can just multiply both sides of the equation by s squared, and I can multiply both sides of the equation by dt. Okay, so we want to get variables on different sides. Okay, so get variables onto different sides. Okay, and remember, k is not a variable. K is a constant. Not a variable. So it really doesn't matter where it ends up. It is not a variable. All right, so if I multiply both sides of this equation by s squared, I'm going to end up with my s squared over here on the left, s squared ds. And on the right, if I multiply both sides of the equation by dt, I'm going to end up with k dt. Now, in order to get rid of these derivatives, these parts of the derivative, what I can do is I can integrate both sides. So I'm going to integrate both sides of this equation. So if I integrate s squared ds, see, doesn't that look familiar? That's going to be equal to integrating. If we do something one side, we got to do it to the other side. We're going to integrate this side, k dt. Remember, k is just a constant. It's just a number. So when we integrate it, the k is just, we're just going to keep it, right? So I'm going to end up with k. And then dt, you can think of this as 1, the number 1. 1 dt would just be t. Okay? And remember, you can always go backwards to make sure you're doing it right. What's the derivative of kt? If I take the derivative of this, it would just be k. Bam, there it is. All right, so here I have s squared. So the derivative of that would be 1/3 s to the third, because I add 1 to the exponent and then multiply by the reciprocal of that new exponent. Okay, so since this is an indefinite integral, I would then have a plus c, a constant of integration. So I would have a plus c on both sides, but then I could move one of my plus c's to the other side, and I could add them together and end up with another c. So when we do the solving of differential equations, don't worry about putting plus c and plus c on both sides. Instead, at the end, we're just going to write 1/3 s cubed equals kt plus our constant of integration. We just tack it on at the end. Now, if we had been given a value that satisfies this equation, if we had been told that we know that there is an initial value or there is some number on this function, and they had given us the s and the t values for that, and they would, for this one, they'd have to give us the k value as well. Then we could solve for the constant of integration. But for this particular one, this is kind of all we can do. We don't have enough information to take it any farther. So our goal here was to get rid of the derivatives, okay, to get rid of the ds and the dt, and that has been accomplished. So now we have a function that no longer has any derivatives in it. All right, we're going to do our next function, next differential equation is coming from the book. So this one is in the book as well. There's several examples in the book. In this one, it is going to give us a value that we are going to be able to solve for the constant of integration. Okay, so our next example is we have our differential equation is y dy dx. Okay, so that's y, some function y times the derivative of y in regards to x is equal to x squared plus 1. So I realize this is totally out of context. We have no idea what kind of situation that is, but we're not going to worry about it right now. Right now, we're just learning how to manipulate the numbers. And then eventually you're going to be doing more problems like this one, where you have to write the equation first before you can solve it. So that way you get some context. Okay, this one is just completely decontextualized. And we are going to be given y of 0 is equal to 4. And another way of saying that is that there is a point in this function. We're going to be solving for the function y. We're going to be eventually getting this to say y equals. And we know that there is some point that when x is 0, y is 4. Okay, so this little thing right here means, okay, what does that mean? It means this. Okay, so this is what you would see, what the problem would give you in the book. And this is kind of how we translate that, right? So this means that there's this 0.04, which we're going to use to help us find our constant of integration. All right, so just like we did on the previous problem, we need to get all of our letters to like sides. So I'm going to leave my y's on this side. Look, I have y dy over here. I just need to get rid of the dx. So I'm going to multiply both sides of the equation by dx. So the dx is going to end up over here. Okay, so we're going to end up with y dy is equal to, notice when I bring the dx over here, everything here gets multiplied by the dx. So I have x squared plus 1 dx. Okay, I am going to integrate this, but before I integrate it, I'm going to go ahead and get rid of those parentheses. So I'm going to rewrite this again. Y dy is equal to x squared dx plus 1 dx. And now I'm going to integrate both sides of the equation. So I'm going to integrate y dy, and I'm going to integrate this side, x squared dx. And I can, when we have the integral of the whole side, I can separate it into the integral of each of the parts, 1 dx. All right, so now we're going to take our derivatives. So these are nice and easy. They're all just using the power rule in reverse. So this one is going to become 1/2 y squared. This one's going to become 1/3 x cubed. And this one's just going to become x. Okay, and now at this point, I can put on my constant of integration. So plus c. Now we're going to solve for c. Solve for c by substituting the information we were given at the beginning. For my x and my y. All right, so my x is 0 and my y is 4. So I'm going to put that in. 1/2 4 squared is equal to 1/3 0 cubed plus 0 plus c. Okay, and now if I simplify that, 4 squared is 16, half of 16 is 8. 0 cubed is 0, 0 times 1/3 is 0, 0 plus 0 is 0, 0 plus c is c. So my constant of integration is c. So my solution is going to be, I'm going back up to here, I'm going to change my c to an 8. So my solution is 1/2 y squared is equal to 1/3 x cubed plus x plus 8. And so notice I've gotten rid of all of my derivatives. I've gotten rid of all my rates of change. And there it is. So we've solved that very decontextualized differential equation. All right, last example. The next one, we're going to take it one step further. And this is, the next example is really most similar to your homework. Okay, so these are kind of building on level of difficulty. So of course, I have to give you really hard problems for homework, right? So the next one is building on that. So let me turn the page in my notes, make sure I don't make a mistake. Okay, so our example here. So find the solution. Oops, can't see that. Find the solution in the form y equals f of x. So notice on the previous problem, we left it in y squared form. Okay, over here, we left it with the y squared. We didn't solve for y. We didn't write it as a single function. We wrote it as a function squared, okay? So most of the time, you want to take it down so that it says y equals, okay? So we're going to do that on this one. So when we do this next one, we are going to be, for my scratch paper, we are going to be solving for y once we get down to it, okay? So find the solution in the form y equals f of x to the differential equation dy dx. Okay, there's my derivative. So that's some rate of change, rate of how y is changing in respect to x is equal to 6 times x squared times y. Again, decontextualized. We don't know what they're talking about here. And we're going to be given a point. Given y equals 2 when x equals 0. So this is, you can see x is 0. That means it's like a starting point because x usually represents time. That's usually our independent variable. So at time 0, our y value is 2. Okay, so that's pretty common. In the previous problem, we had that same thing. X was 0. That usually means time at time 0. So this is your starting point, basically, at time 0. Y is 4. So they're kind of giving us like the y-intercept. That's a real common thing to do, apparently. All right, so here we go. So we want to get the y's to one side and the x to the other. Okay, we might want to write that down just to remind ourselves. Get the y's to one side and the x's to the other. Okay, right? We're going to separate them, make them part ways. Okay, so in order to get y by itself here, dy, I'm going to multiply both sides by the dx. So I'm going to move the dx over here. So I'm going to be left with dy is equal to 6x squared y dx. Okay, so I've just multiplied both sides of the equation by dx. So the dx ends up over here. Now I need to get rid of this y. So to get rid, notice everything's being multiplied here. So I can't minus the y. I have to divide by the y. So we're going to divide by y. And I end up with dy over y is equal to 6x squared dx. Now, the left-hand side here, that's not how we want this written when we go to do the integral. That kind of looks kind of weird. We don't want anything underneath the dy. So we're going to separate this out. We're going to write this as 1 over y dy, because then we know how to take the integral of that. This side looks fine. We know how to integrate that side. That one looks quite normal. Okay, so this is separable. We were able to separate our x's and our y's. If this y had been added on and then I had to subtract it over here, we wouldn't know what to do. Okay, so we're only learning a technique for solving one very particular type of differential equation. These are ones that are, sorry, I lost my train of thought. They are proportional. They're proportional. So basically, we have things being multiplied together on one side. We don't have a lot of things being added or anything like that. Okay, so different things happen, like the example that we saw in Khan Academy, the first one with the second derivative plus the first derivative plus the function. that gets solved in a totally different way. Okay, so we're just learning one specific case of differential equations right now, and we'll learn more later. All right, so now we're ready to integrate this. So we're going to integrate 1 over y dy is equal to the integral of 6x squared dx. So 1 over y, if you don't remember what that is, we actually did it in the warm-up. Okay, so if you look back at how we did the warm-up, that, when you integrate it, that is equal to the natural log of y. And then on this side, this one's just normal. Add 1 to the exponent and multiply by the reciprocal. So 1/3 times 6x to the 3. And then I can add on my constant of integration. Okay, so now I can go ahead and I can put in my numbers to solve for my constant of integration. Okay, so now we're going to solve for c. So we want to solve for c. Okay, we're going to use the point 0, 2. 0, 2. Okay, so we're going to go back up here and we're going to grab our 0 and our 2, and we're going to substitute those in. So the natural log of y, well, y now is 2. So natural log of 2 is equal to, let's see, 1/3 of 6 is 2. So I'm going to go ahead and simplify that to 2. 0 cubed plus c. Okay, well, this is easy. 0 cubed is just 0. 0 times 2 is 0. So c is equal to the natural log of 2. All right, so I'm going to go ahead and put that back in. So where am I right now? I now have my solution right now. And we're not done, by the way. My solution at present is natural log of y is equal to, remember 1/3 of 6, that's 2. So 2x cubed plus c, which is the natural log of 2. Okay, so now we're going to get kind of fancy. We want to solve this for y. So we want to rewrite this in exponential form in order to get rid of the natural log. Okay, and this is going to get a little tricky, but pay attention. This is going to be useful. I am kind of running out of room here, so but I don't really feel like going to another page, so I'm going to do this. I'm going to do this. And then I'm going to bring this. Now we're going to solve for y. Solve for y equals form. Okay, we're going to put it into y equals form. All right, so we're going to take this back up here. We're going to take this answer, natural log of y is equal to 2x cubed plus the natural log of 2. Okay, if you want to turn the page, by all means, turn the page, but you guys all write smaller than me, so shouldn't be a problem. Okay, so to change this to exponential form, I'm going to take my natural log here. Remember, the base is e, so this means e to the, this is all the exponent, equals y. So I'm going to rewrite this. Remember, this is a base e, so I can say e to the 2x cubed plus natural log of 2 is equal to y. And you could say, done! I got y by itself. But if this were a problem in the book and you were to look in the back of the book, that would not be what you would find because this can be simplified. So when you have an exponent with addition in it, that's the same as writing e to the 2x cubed times e to the natural log of 2. Right? Because if I'm multiplying two exponential expressions that have the same base, I can add the exponents, right? If I added those together, I would get that. And now this little one right here, e to the natural log of 2 simplifies to just 2. And I could go through the proof right now, but I'm not going to, okay? This just simplifies to 2. And I believe in our formula packet, we actually have that shortcut down. It'll actually show you like e to the natural log of a just equals a. I'm pretty sure that's in our formula packet. All right, so this just equals 2. So I have e to the 2x cubed times this whole thing just equals 2. It's equal to y. So let's flip this around, put it in a more natural order. So my final solution, written all beautiful, as good as we can get it, my final solution is going to be y equals 2 times e to the 2x cubed. Ta-da! All right, so that is that. And you are going to have problems from the textbook. Sorry, we've gone past math space. Math space cannot keep up with us anymore. You're going to have to do some problems from the book. All right, that's it. Let's stop this video.